Next we have part D, in which we identify any element x in the original space x with the corresponding formal limit of x, which is the formal limit of that Cauchy sequence, all of whose elements are equal to this x. Then this formal limit is an element of x bar. We have to show that this is a legitimate identification by verifying that for any 2 points x and y in x, they are equal if and only if the corresponding formal limits are equal. And once we show that, then we have to show that with this identification, the distance between x and y as calculated in the space x, that means using the metric d, is the same as the distance between them as calculated using dx bar. And that allows us to consider the original metric space x comma d as a subspace of this other metric space. Solution: one half of this double implication is trivial. If x and y are the same point, then obviously the formal limits also are the same. Conversely, let the formal limits be the same. Then by the definition of two formal limits being equal, this limit will be equal to 0. Limit of d of x comma y as n approaches infinity. You do not see any n here because you don't have any n here. In the general case where you have xn and yn, here you would see d of xn comma yn. But then this is a constant sequence of real numbers which converges to that real number d of x comma y. So that's how we find that d of x comma y is 0. But d itself is a metric, so that's why this implies that x is equal to y. So that means the reverse implication is also true. And next we take any 2 points x and y in x and we consider their distance as calculated by the metric d. But again, just like this calculation, this is equal to the limit of this constant sequence, all of whose terms are equal to this real number. This, however, by definition of the metric dx bar is equal to the dx bar distance between these two formal limits, limit of x and limit of y. But because of our identification, in place of limit of x, we just write x, and in place of this, we just write y. So whether you consider these points x and y as points in x, or whether you consider them as points in x bar via this identification, the distance does not change. So in that sense, the metric space x, where is it? I don't see here. Anyway, the metric space x is a subspace of x bar. And then we have part E, where we have to show that the closure of x in x bar is x bar itself, which explains the choice of notation, because this is how we denote closure of a subset in a metric space. Note carefully that x originally is not a subset of x bar, but because of this identification, it has become, or it can be considered as a subset of x bar, and in fact a subspace of x bar. We start the solution by taking any point z in x bar. What does it mean? It means that z is a formal limit of some Cauchy sequence xn in x. Now if we can show that, then z is also a legitimate limit, not just a formal limit, an actual limit of some sequence in x, then by a previous theorem, this z will be an adherent point of x, and so it will belong to the closure of x. That's what we are going to do. And our candidate for that sequence, whose limit will be z, is this xn itself. And to show this, we first choose a positive real number epsilon. Because our sequence xn is a Cauchy sequence, for this epsilon there exists a positive integer j, such that the distance between xn and xm is at most epsilon, that means less than or equal to epsilon, for all indices n and m greater than or equal to j. So for each integer n greater than or equal to j, this calculation is true. dx bar distance of the formal limit of xn as m approaches infinity and z. But what is z? Z is this formal limit, limit of xn as m approaches infinity, which is equal to, by the definition of this metric dx bar, equal to this ordinary limit of d of xn comma xn as m approaches infinity is less than or equal to epsilon. And here we have somewhere used lemma 6 for 13. All of this looks extremely confusing. What's going on? So let's try to understand it more clearly. When we say for each n greater than or equal to j, we mean that we are fixing n. For example, say one of the values of n is j itself. You have fixed j, n equal to j, now that is j, that's not changing. If you do that and then consider this sequence, this entire dxn comma xn, where now n is j, then it becomes a sequence of m. M changes, right? This n stays fixed and that is j. This entire thing now becomes a sequence of real numbers where the index is m. And all the terms of that sequence are less than or equal to epsilon. So by the comparison principle, this is the comparison principle if you recall, the limit of this sequence, which we already know exists, will also be less than or equal to epsilon. Okay. This, however, is equal to this. Actually, here you are looking at formal limits of two Cauchy sequences. One of them is the ordinary sequence xn, where we have used another name for the index instead of n, because n has been used here somewhat differently. So we are calling the index here m. So this is just the formal limit of that sequence as m approaches infinity. The other Cauchy sequence, however, here is the constant sequence, all of whose terms are equal to xn or that xj, that thing. So that there you do not see the index m, but it's there hidden. It's not present here, but because it's the constant sequence, so m does not appear there. But still, it's the Cauchy sequence because it's a constant sequence, so it has a formal limit, and that is this itself, or in other words, xn. Okay. This, however, is z. So what have you found here actually? You have found that for each such n, the distance between the formal limit of the constant sequence xn as m approaches infinity and z, as calculated using the metric dx bar, is at most epsilon. And this implies, this entire calculation implies that limit of this formal limit of xn as n approaches infinity is that z, and this is a statement in x bar. How? Well, how did you start the calculation? By choosing any epsilon greater than 0. For that, you have found that there exists a positive integer j, such that when your n is at least j, then this sequence where the index is n behaves like this. Its distance from z is at most epsilon for all such indices n greater than or equal to j. That is why the limit of this sequence as a sequence depending on the index n as n approaches infinity is z, and obviously because here we are using the metric dx bar, so things are happening in x bar. What type of sequence is this? In this sequence, a single term is a formal limit, right? And that formal limit is this, which depends on n. And that itself is a formal limit of what? formal limit of the constant Cauchy sequence, all of whose terms are equal to that xn like that. And that is why z belongs to the closure of x in x bar. But z was any element in x bar, so that is why the closure of x is equal to x bar. But exactly how? I mean, are we not still a little not convinced about this? How do we get this line from this line? We will get this line from this line provided that this becomes a sequence in the original space X. Is it? Yes. Because if you recall the identification, these terms, individual terms of this sequence that you get for different values of n are just xn. That is already a sequence in X. So in that sense, in the sense of that identification, you have found a sequence in X whose ordinary limit as calculated in the metric space X bar is Z. That chosen point, arbitrary point which was chosen from X bar. And that is why that becomes an adherent point of X in X bar, and that makes the closure of X the entire X bar. And finally, we have part F also, where we have to show that formal limits agree with actual limits. So if x then is the Cauchy sequence in the original space X, then you can think of it as a Cauchy sequence in the space X bar also via that identification. With that, we have to prove that limit of x then, that is ordinary limit, is actually equal to the formal limit of x n. Really, there is nothing new to prove here, so instead of a solution, I give you this hint. See the solution to part E. And with that, this section is completely over. In the next analysis video, we are going to start compact metric spaces.